Well, a warm welcome indeed. Thank you for being here. Get yourself ready with a notebook. Grab a pencil or pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we're looking at a rational function. We're going to be discussing the inverse of this function. I'd like you to find the inverse of this function. Give it a shot first by yourself before you see how we did it here. So we have a basic rational function here. You'll know that rational functions have a domain restriction. If you're unfamiliar with domain restrictions, check out my video on the 3 main types of domain restrictions. I will put the link for that in the description. I'll give you a glance at what I want you to do in this problem. In this video, we're going to cover finding the inverse, stating the domain and range for both this function and its inverse, which I'll just call f inverse. Put that somewhere. And then I want you to identify the intersection of their graphs. So I'm going to do that with Desmos. If you can graph it by hand, though, I think that's great. It would be excellent if you have the diligence to graph this by hand and identify their intersection. Because we're humans and we don't graph perfectly, it could be difficult to get the most accurate intersection. So that's why I totally strongly encourage using Desmos as support. So you can graph the inverse and the function on Desmos, and you'll get a chance to see where they intersect there. All right, go ahead and pause the video if you want some time to work on this. But without further ado, let's get started. So in order to find f inverse, a lot of times what we do is we switch the x and the y, and we sort of solve for the y all over again. So before we get what f inverse is, let's just mention that y equals 2x plus 5 over x minus 3 is going to change. It's going to transform into x equals 2y plus 5 over y minus 3, where now the y stands for the inverse. So because we've switched, let's make this a little larger, because we have switched the x and y, we now identify y as f inverse. There we go. So we're going to solve for the y in this equation, and that's going to result in us getting an expression for f inverse. It looks kind of tough because we have y on the top of this fraction and y somewhere in the bottom of the fraction. So here's the technique. We're simply going to multiply both sides by y minus 3. We need to get y out of denominator since we're trying to solve for y. We can't solve for a variable when it's in the denominator of a fraction, so we need to move that denominator by multiplying both sides. And, oops, let's use a better color. 2y plus 5. Now, at this point, we want to distribute. I know it seems like it's going to complicate things more, but really what we need to do is we need to get the y isolated, and I cannot isolate the y if it's in a denominator. That motivated the first step, and I cannot get the y by itself if it's in these parentheses, so that motivates the next step of opening up the parentheses, distributing the x, and now we have, I don't know, maybe it's a yucky equation to you, but really what we have here is an equation with the variable in 2 places, but not in the denominator and not in a parentheses. That's very key. We've unlocked the y expression. Now let's move everything with a y in it on one side. So I actually want to move this that way. This is going to give me xy minus 2y. Anything without a y must go on the opposite side of the equation, because I want to isolate the y. I don't want anything without y. I'm going to move it over to the other side, and we have 3x plus 5. All right, we're almost there. Now we do want to factor the y out. Now that everything on the left side of the equation has y in it, I can factor the y out, and that's going to allow me to take these multiple terms with y in it and just extract y from all of them simultaneously. And you can imagine the last step is to divide the x minus 2. I don't want it attached to the y. I want it to be on the other side. Now I have to use division, not subtraction or addition, in order to achieve that. So this is going to give us 3x plus 5 over x minus 2. And that is our inverse. All right. So there's our inverse. Part A is done. I want to take a moment to discuss the fact that rational functions have this domain restriction. I know I mentioned it, and I kind of plugged my other video in there. But I do want you to mention the restrictions here, because we're going to talk about the domain. The restriction here is that x cannot equal 3, right? But I also want you to think about the horizontal asymptote, because in a rational function, we often have these horizontal asymptotes, and in this case, we'd have a horizontal asymptote at the line y equals 2. How do I know that? Well, we can find the horizontal asymptote by identifying the relationship between the degree of the numerator and the degree of the denominator. The numerator and denominator have the same degree, therefore we take their leading coefficients, their leading terms, 2x and x, and we make a ratio. And this ratio gives us the value of the horizontal asymptote. Remember, that means that in the range, the y value cannot equal 2. That becomes very important when we consider this for the inverse. The inverse is 3x plus 5 over x minus 2. So for the inverse, I need to make sure that x does not equal 2. Sound familiar? Where does the 2 come from? Well, that's just like how we had that y cannot equal 2. Remember that inverses switch the x and y. So on the original function, if the y value is not allowed to be 2, then on the inverse function, when we switch the x and the y, now on the inverse function, the x is not allowed to be 2. Makes sense there. Let's also discuss the horizontal asymptote. We have the same degree on top and bottom, which means we can compare the leading terms, 3x over x. That gives us y equals 3, which means y cannot equal 3 for the inverse function. And if you look at the x and y restrictions, they are switched between the inverse and the original function. The original function does not allow x equals 3, and the inverse function does not allow y equals 3. The original function does not allow y equals 2, and the inverse function does not allow x equals 2. So if we state the domain range for f, we would say the domain is x does not equal 3, and the range is y does not equal 2. There are other ways to write that if you really want to. You can say negative infinity to 3, union 3 to infinity for the domain. And for the range, you can say negative infinity to 2, union 2 to infinity for the range. If you'd like to put intervals versus simple restrictions of values, that's fine. And for f inverse, we're going to have this switched. So for f inverse, we're going to have, if you want to call it negative infinity to negative infinity to 2, that could be described on the domain. So the domain x cannot equal 2. And for the range, we could say negative infinity to 3, union 3 to infinity, where the range is that y cannot equal 3. Okay, very good. Now, the last thing to do is to identify the intersection of their graphs. I would like you to try to graph these or try to sketch these by hand, just because it's good practice. You need to know how to sketch things by hand. But we're going to go over to Desmos and make this a little bit easier on ourselves, yeah? So y equals, not hy, y equals a fraction, 2x plus 5 over x minus 3. And then we have another function, which is the inverse, y equals 3x plus 5. Let's make a fraction out of it, 3x plus 5 over x minus 2. Did I get that right? I could have made a mistake. I'm prone to making mistakes sometimes. Yeah, there we go. And you'll notice this is quite interesting. There are 2 points of intersection here. Yeah, there are 2 points of intersection. We have 5.8541, 5.8541, and negative 0.8541, and negative 0.8541. What do you notice about those points? They have the same x and y value. And that's because the intersection of an inverse and its function should always occur on the line y equals x. After all, these graphs are a reflection of each other across that line y equals x. If we wanted to solve this algebraically, by the way, we would have to say 2x plus 5 over x minus 3 equals 3x plus 5 over x minus 2. So we would cross multiply these and get 2x plus 5 times x minus 2 equals 3x plus 5 times x minus 3. And of course, we can solve this quite easily. These are just some basic FOIL practice, FOIL multiplication here. Minus 4x minus 15. Move everything to one side, and we get a quite nice quadratic, to be honest. It's not the worst in the world. We can't factor this, though, so we would have to use the quadratic equation. Here we go. If I'm going too fast for you, you can slow the video down, and then maybe I'll be talking like this. I'm just kidding. My voice will probably slow down if you slow the video, though. I wouldn't be surprised. So here we have 25 plus 20 over 2. For two solutions, we have 5 plus the root of 45 all over 2, and we have 5 minus the root of 45 all over 2. Now, what's the root of 45? Well, it's not a particularly nice number necessarily, but it is rather close to 6.8. You know, it's between 6.7 and 6.8. I believe 6.7 squared is like 44.89 or something. So let's pretend that this is like 6.7. I don't know. That seems reasonable. So this would be something like 11.7 over 2, which is approximately 5.85. Sound familiar? And this is approximately 5 minus 6.7, which is negative 1.7 over 2, which is approximately negative 0.85. Sound familiar? I mean, it's pretty close, right? Can I get some credit for that? 0.85 and 5.85. They're pretty close. So these are our approximations. These are decimal approximations. Do not use decimal approximations unless requested. Otherwise, you would leave your answers like this. 5 plus rad 45 all over 2, and 5 minus rad 45 all over 2. Yeah. Okay, so there's a little bit of a quadratic exercise at the end there, but the point of this problem is to identify how to find the inverse of a rational function. We simply follow the mechanics of switching your x and y, solve for the y all over again, and Bob's your uncle. Do everything carefully. There you go. All right, I think that's enough blab out of me. I'll see you guys next time.